Good morning, everybody. Back at it again. You can put a green check mark into chat so we can verify you're hearing us, seeing us, and you're alive and well. We'll get started. Perfect. A few people putting those in. We'll start with any questions you might have had from the learning guide from yesterday. And then I think tomorrow's class, we will spend the day looking at the first 3 units. So I wasn't sure if I wanted to do that tomorrow or the next day, but I'm thinking Wednesday is as good of a day as any. So we'll go through any sort of review questions you might have tomorrow. But for now, anything you have in regards to this Unit 4 stuff we've been doing, a lot of which you've probably seen before, maybe some of it's a bit new. It just kind of depends on what your Math 9 teacher did. There's a few people without green checks in chat. Maybe they're sleeping quietly in their beds. Alex, you had a question from last day that I didn't get to, and I apologize for that. So I'm hoping the one that you just put in there was the one that you forgot about last day. Perfect. More green checks. That's looking good. All right. So just a couple of questions then to go through. That's it. I'm happy to see that. Hopefully you guys are kind of understanding this stuff a little bit. And again, trying to go as slow as I can so we don't get too mixed up with reviewing for the midterm and then going through this unit. Really, the stuff that we're doing today is pretty straightforward. And then once we get into Thursday's stuff, it gets a little bit more tricky. So definitely new stuff on Thursday, but then that'll just be one sort of new thing before the midterm and we should be good. All right, so we have a bunch of questions in here. Expanding polynomials 2C and E, page 5, 4B, and page 4, 2C. Let's get to these guys. So I don't know which page is first. Page 5, 4B, page 4, 2C. Let's go to page 4, 2C first. 1, 2, 3, 4. So we're going to expand that little guy. And then Alex had a question, page 5, 4B. Okay. And then Taylor, expanding polynomials 2C and E. Okay. 2C. Okay, so that was a similar question that I think Jade had. Avery is asking a question about how much of Unit 4 will be on the midterm. So the stuff that we did last day, so the stuff that I'm going to do right now, the expanding polynomial stuff, that's going to be on the midterm. So I started making it yesterday, and I'm thinking it's going to be 25 questions, multiple choice, roughly about, I don't know, 6 or 7 questions for the first few units, units 1, 2, and 3. And then just a couple of questions from Unit 4, just to the expanding stuff that we're doing right now. So there definitely won't be a focus on Unit 4. Just like, I think there's like maybe 2 or 3 questions from Unit 4. So it is on there, but it's not a prominent part of the midterm. All right, so the first thing we had was page 4, number C here. So when we were expanding these things, what we're going to do is multiply everything in the first bracket by everything in the second bracket. Now, if we have binomials, we can use the acronym FOIL. But in this case, we don't have binomials. We have a binomial and a trinomial. So what we're going to do is take this 3, multiply everything in the second bracket by the 3, and then we're going to take the negative a, and then multiply everything in the second bracket by the negative a. So maybe I'll stick with these 2 colors here. 3 times 2a squared is going to give me 6a squared. 3 times negative 4a is going to give me negative 12a. and 3 times 2 is going to give me 6. Now, that's the first term multiplied by all 3 in the second bracket, the trinomial. Then I'm going to do the negative a. Remember there's like a negative 1 here, so if you're multiplying the 1 by the 2, you're going to end up with negative 2. So I'm going to put a negative 2, a times a squared is a cubed. I add my exponents. Negative a times negative 4a is going to be a positive 4a squared. And negative a times positive 2 is negative 2a. So there's always 2 steps to these problems. You do the multiplication, so you kind of expand, and then you have the simplify. So it's expand and simplify. When I simplify, I'm combining like terms. So if I have any a squareds, I need to combine them together. If I have any a's, combine them. So I see a squared here. I see, oh, sorry, that's an a cubed. Another a squared here. How about a's? I have negative 12 there, negative 2 there. And then the other terms are just kind of one-of-a-kind sort of things. So what I'm going to do is write them with the largest exponent first, and that's just kind of how we do things in math. So I'm going to write this as negative 2a cubed, and that's this guy here. Then I look for my a squareds. I have 6, and then I'm going to add 4. So plus 10a squared. So that gets rid of my a squareds. Then if I have any a's, so I have negative 2 and negative 12. So I have negative 14a. So that gets rid of these guys. And then I have this just lonely little plus 6 here. So I've expanded and simplified, and that is what I ended up with. So hopefully that is right, and I have answered your question. Maybe the answer might be wrong, or we're on the right track there. So that's the first one. The second one that somebody asked about, did Taylor, you asked about letter E, is that right? Yeah, E, perfect. You know what, Abby? I have seen that somebody brought me their review in and it was printed, and it's just kind of like a formatting thing. So what I can do is I can go and convert it to PDF, and then we can see if that works better. So I know it's happened to a bunch of people. It might be like a Word version sort of thing. Sometimes when we put in the equations, we use something called the equation editor, and if maybe you don't have that installed on your computer, it's not going to appear properly. So yeah, it happened to Chloe. Anyone else running into that problem? See a few people typing. So yeah, I'll do my, oh, Avery too, perfect. Well, not perfect, but it's not just you. I'll do my best to convert these things into PDF, and then hopefully you don't run into that problem. I don't think it should happen as much. I'll do E really quick here, and then we'll move on to the next page. So this one's a little tricky because of all this stuff happening kind of in the middle here, and you got to really wonder what's going on and think about, you know, what numbers are there, and why is the 3 and the 4, and how to maybe simplify that. Geez, I'm taking a second. I haven't done a question like this in a long time. So we need to follow BEDMAS. That's the important thing here. So anything inside my brackets, no. I don't have any exponents. So I guess the next thing I need to do would be my multiplication. So I'd be really tempted to add the -3 and the -4 here together. But I'm thinking that we can't do that because we need to do our multiplication before we can do our addition and subtraction. Part of me is saying that's wrong. I'm really curious to see how this works out. We're going to multiply the 2 through the bracket here, and then what I'm going to do is multiply the -4 through the bracket here. And then I'm just going to bring the -3 down, and we'll see kind of what happens with that. It just kind of hangs around. So 2 times 4x gives me 8x. 2 times 3y is -6y. Then I have this -3, which is just hanging around. And then -4 times +2 is -8, and -4 times y squared is -4y squared. At this point, I'm going to combine any like terms I have. Just a bit of a strange question. What do I have? Nothing that's like except for the -3 and the -8. So I can just combine those together. So I'm going to put my y squared out front. -4y squared, -6y, plus 8x, and then 3 and 8, both negative, give me 11. I don't know that I've ever done a question like that before with this stuff happening in the middle with the -3 and the -4. So it's a bit of a strange one. So that's that. There's a couple questions, or maybe one on the next page. 4b. So use the rectangle below to demonstrate the area method for expanding and simplifying. This is just a kind of an expansion question. You're just multiplying these things together. Now, the course, the answer key says it's -4y squared minus, so is that what I ended up with? Plus 8x. -4y squared minus 8x. 6y minus 11. I'm thinking that we did okay then, so we'll just go with it. Order of operations wins again. The actual curriculum says to be able to do this sort of multiplication and expansion with sort of graphic things like squares and rectangles and things like that. I'm not a huge fan of doing it that way, and there's not a big emphasis on it because basically it's something that you generally don't use a lot of moving forward in your math. So like in grade 11 and 12, and if you continue on doing math in university, you generally won't see these types of examples just because it's kind of another way of doing something. It's hard to explain. So what I'm going to do is basically I don't even really remember how they use the area, so I'm just going to expand it and go from there. And I have no problems if you do the same thing. So multiply the first term by the 3, then the second term by the 3, and then we're going to see where we end up. Now, the reason we can say this is an area is if you think about this side, if I told you this side's length was 12, you'd be like, okay, it's 12 units long, that makes sense. Now, if I said this side's length is x minus 5, you'd be like, well, that's a bit strange. How do you get that? Remember that x is just a variable. It's holding the place of a number. I could say, you know, x is 12, and you'd put in 12 minus 5, and you say, okay, this length's 7. That makes sense. But when I say the length of this side is x minus 5, that doesn't really make a lot of sense. And then if I said the length of this side is 4x squared plus 3x minus 3. You'd say, well, that's weird. But then again, if you remember that x is just a number, so if I put in a 1 here and a 1 here for x, and I put in a 1 here for x, I'd get, you know, negative length, which would be strange, but I'd get 4 plus 3 minus 3. So I just end up with a length being 4 here. And that's kind of where this area idea comes from. When we find the area of a rectangle, it's just going to be area is the length of the rectangle times the width. So here's my length, and here's my width. If I multiply them together, theoretically I should end up with the area. It's just kind of a, I don't know, a different way of talking about these sorts of things. So if I do the multiplication, I get 4x squared times x is 4x cubed. And then 3x times x is 3x squared. And negative 3 times x is negative 3x. So that's the x multiplied by everything. And then I'm going to multiply the negative 5 by everything. So negative 5 times positive 4 is negative 20x squared. Negative 5 times positive 3 is negative 15x. And negative 5 and negative 3 is positive 15. I have some like terms I need to combine. I have a couple x squareds here. And then I have a couple x's as well. So I'm going to combine those all together and just rewrite this. So I get 4x cubed, 3x squared minus 20 is negative 17x squared. Negative 3 and negative 15 is negative 18x, and then plus 15. So somebody asked for the area of this rectangle. Well, you could just say, okay, multiply the length by the width. I'm multiplying two things together. They just happen to be a binomial and a trinomial. You do the multiplication, you end up with the answer, and then that's the area. Now, it's important to remember that x is just a variable. We could substitute any number we want in for x and just end up with a number for an answer. But when we have all these x's and y's representing lengths, it's just kind of strange, bit of an abstract concept. So there you go. That's how you can represent the area of a rectangle using these polynomials. Just want to make sure I didn't forget anybody's questions. Page 4C, 5, 4B, 2C and E. I think that's it. Perfect. In the course, I guess I could just flip over to it. I kind of did lessons 2 and 3 together. And lesson 2 was expanding polynomials and lesson 3 was expanding special polynomials. So I mean, they're the same thing. I just put all of the sort of questions into one sort of example. You're expanding though, that's what it is. You're multiplying these binomials and trinomials together, and then you're combining like terms, and that's basically all you're doing. So I don't know that it needs to be broken into 2 lessons, which is kind of funny because the lesson I'm gonna do today probably should be broken into 2 lessons, but I didn't. So let's look at, I know it's technically the 3rd lesson we've done, but I'm calling it lesson 4 because we kind of did 2 and 3 together. So I'm hopefully not confusing anybody with that. Lesson 4 is factoring polynomials, and factoring is a word that kind of strikes fear into Math 10 students because when we get into the next section, section 5, this factoring stuff gets a bit tricky. It's kind of one of these light bulb concepts, and you'll be sitting there and you'll be struggling, and all of a sudden your light bulb will go off in your head and you'll be like, oh, this all makes sense now. It's just so easy. It's the same process over and over again. It takes some practice before you kind of get it because it's a bit of a different idea. So first of all, let's talk a little bit about some vocab we're going to use. We'll look at some really, really basic examples and then we'll kind of leave it there. And then next day, we'll kind of get into the meat and potatoes of Unit 4, factoring. So first thing I should talk about is what does the word factor mean? You likely haven't heard of factoring before. It's not something that comes up in Math 9. So the word factor is a bit of a new idea, I'd imagine. So when we talk about factoring, all it means is to write as a product, and that's it. This is kind of one of these things where math kind of takes on its own language. When we use the word factor and when we define it with another word, product, which can be kind of simplified a little bit further. So what do we usually mean when we say something like product in math? What is kind of the mathematical operation for product? So I'm going to put down an example here. Just how do we have a product? What does product generally mean Anyone remember? Answer? Yes, answers can be products. Generally speaking, when I say you take the product of two numbers, the product is what you produce, but what mathematical, like if we're talking in terms of bed mass, what bed mass letter are we going to use when we're talking about product? I can see I'm a bit off track here. When we say product, what we really mean is multiplication. So if I'm saying, hey, write something as a factor, and that just means to write it as a product. So if I take the number 20, for example, Alex was on it, good job, Alex. How do I write 20 as a product? What numbers can I multiply together to give me 20? There's lots of different ways I can do it. I can multiply 2 by 10, I can multiply 4 by 5, I can multiply 2 by 2 by 5, and I've written 20 as a factor. So these are the factors of 20, 2 and 2 and 5. There's other factors of 20. Alex has written a few in chat here. We have 4 and 5, 10 and 2, 20 and 1. Those are all, products. So multiplying, that's factoring. If we factor something, we're taking the number and saying, what numbers can I multiply to get to that thing? So don't be afraid of the word factor. It's just a pretty basic idea. The questions get harder, but that's just what it means. So a prime number is something you've encountered before, I'm sure. What's special about prime numbers? We talk about primes. Primes are really important for things in like cryptography and things like that, codes and breaking codes. Primes have special properties. So we use primes for things like that. Lily is jumping in and out of chat. Prime numbers have only factors of 1 and themselves. 2, 3, 5, 7, 13. Those are all excellent examples of prime numbers, and your definition is spot on. So let's use it. We'll go with a whole number. With only 2 factors. And those factors are itself and 1. So 1, 2, and 3, 5, 7, 13, those are the ones you included. Coincidentally, 2 is the only even prime number. All other primes are odd. Kind of an interesting little math thing. So there you go. Composite number is not a prime number. That's right, Alex. Composite and a prime are different. What makes them different? Composite number is not something that really comes up in math a lot. I guess it's in here because we run into it a bit in grade 10. You might see the word, but it's probably not one you'll encounter a lot. A composite number is a number with 3 or more factors. So I don't know, let's pick a composite number. Something like 8. What are the factors of 8? Well, we have, I guess it's not really equals. Factors of 8, we could have 1, 2, 4, and 8. Those are all of the factors of 8. So that's composite number because there's 3 or more of them. 3 or more, so 4 by 2, 2 by 2 by 2, and 1 by 8. Those are all of our factors. You can see why we spend so much time asking you guys to be good at your multiplication tables by the time you make it this far, because doing these questions becomes a lot easier when you kind of have a good understanding of multiplication. Prime factorization is something we're going to do actually today. So this is kind of what it sounds like. We're mixing two things together, two definitions, factor and then prime numbers. So a prime factorization is going to be breaking a number down into its prime factors. And we're going to look at a few examples of that. So it's going to be writing a number as a product of its prime factors. So I'm not going to kind of include an example of that because we'll actually do a few in the lesson. The greatest common factor and least common multiple are two other terms. And below these, you might just want to put this in brackets. A lot of times, greatest common factor you'll see as either, it'll say like GCF, and then there'll be two numbers separated by a bracket. That's something that we'll see for greatest common factor. And least common multiple will look something like LCM, and we'll put two numbers in brackets. So these are kind of two terms that come up a lot. Least common multiple could be lowest common divisor as well, so LCD. That's another sort of acronym for the same thing. So what is the greatest common factor? Is the greatest number that divides into each number in a set. And when I say a set, I just mean I give you two numbers, you tell me the greatest number that goes into both of those. And while we're here, the least common multiple wow, just reading my definition, it doesn't really make sense. The least common multiple is that is the same for two numbers. Maybe I can just go off the top of my head. It'd be the smallest number which, no. I'm going to go with what I had. Doesn't make a lot of sense, but we'll go with it. The least multiple that is the same for two numbers. Now that's a terrible definition, so let's include an example, like a really easy one. If I said, what is the LCM of 12 and 21? Basically, you're looking at multiplying these numbers. So if I go 12 times 2, I get 24. 12 times 3 is 36. So 21 times 2 is 42, and then times 3, it's going to be 63. So at what point do these things multiply to a common number? And the smallest number they both multiply to is going to be 84. And we'll look at how we can get that. For now, you'll just have to take my word for it. You can kind of see where I'm going with it. We'll look at a couple examples. All right, so we got some sort of basic definitions out of the way. If you need to go back and refer to them, now you have them. I have a feeling you've probably done prime factorizations before in factor trees. You do spend some time doing it in grade 9 math, if I'm not mistaken. So the first question here says, write the prime factorization of 3,300. And you're going to have sort of two methods you can choose. Now, I prefer the factor tree method. It's kind of how I like to do it. And some of you might like the repeated prime factor division. Doesn't matter. I'll do them both. Pick one you like. What we're always going to do is start with our number up at the top. So 3,300. And when I do a factor tree, I say, okay, what numbers multiply together to give me 3,300? Now, there's no right way to start this. You can just, whatever comes to your mind. As soon as I see zeros at the end of a number, I'm thinking there's going to be some sort of factor of 10 that kind of goes into that. So I'm going to break down this 3,300 into 33 times 100. You could have broken it into 330 times 10, or I'm sure like 33 times something would have ended up, 11 times something might go in there. I don't know. There you go. Once you want to break down the next two numbers you have here. So I have 33 and 100, and I need to break down 33. So the only thing I can think of in terms of breaking down 33 is breaking this into 3 and 11. And then 100, I'm going to break that down into 10 times 10. Now, I know I'm done when I have a prime number. And prime numbers are only divisible by 1 on themselves. So what are my primes here? I have, 3 and 11 are both prime, so I can stop at those guys. But 10 is not prime. I can break 10 down further into 2 and 5, and I'll do the same thing here, 2 and 5. Now this is done. These are all prime numbers, and I can't break it down any farther. So when I've written the prime factorization of 3,300, I'm going to write it as 3 times 11 times 2 times 5 times 5. I'd usually write it in order from smallest to the largest. So that's one way to do it. Another way to do it is repeated factor division, and some of you may prefer this method, so I'm going to show it to you, and you can kind of decide what you want to do. If I have a number like 3,300, and I'm thinking, what is a number that goes into that that's prime? And I see the last digit 0, so I know at least 2 is going to go in there. So I'm going to just plug it into my calculator, divide it by 2, and I end up with 1,650. Okay. So now I'm going to start with this 1,650, and I'm going to say, I could probably divide that in half again, because it ends in 0, and if it ends in 0, I know it's divisible by 2. And that gives me 825. Okay, 825. Well, the last digit's not 2, so I know I can't divide it in half, but I can divide it by 5, because the last digit's 5. I know I can divide by 5. And if I divide it by 5, I get 165. Okay, 165 again. That'll divide by 5 again because it ends in 5. And end up with 33. Now I'm starting with 33. What numbers give me 33? I'm going to probably go with 11. And I end up with 3. And 3 is a prime, so I can't divide anything by 3. I'm just left with 3. So if I look at the numbers I ended up dividing by, including the last number, 2, 2, 5, 5, 11, and 3, they're the same as over here, 2, 2, 5, 5, 11, and 3. So all numbers are prime numbers. All numbers are prime numbers or are made up of prime numbers. Yeah, we can take a prime factorization of any number. we can always break a number down into its prime factors. Even if it is prime, it's just going to be 1 in itself, but technically 1 is a prime factor and then whatever the number was. So yeah, we can always break a number down into prime factors. So we need to kind of write this down. The prime factors of 3,300 using our factor tree. Sorry, I'm gonna take a step back here. I want to make sure we get this right. The prime factors of 3,300 are. So what were the numbers that went into 3,300? Well, we had a 2. That was one of them. We had a 3. We had a 5. And we had an 11. So those were all the prime factors of 3,300. The prime factorization of 3,300 was a little bit different. How many times did each of those numbers appear? So I had 2, and it appeared 2 times. I had 3, it appeared once. I had 5, it appeared 2 times, and I had 11. So all of these things multiplied together would be the prime factorization. So if I plugged in my calculator 2 squared times 3 times 5 squared times 11, I would end up with 3,300. Now you don't need to write it like that. I'm just going to lose this, but that's why we write it that way. Because if we went backwards, we'd want to end up with 3,300 again. Do you guys remember the divisibility rules for each of the numbers? There's some special rules. Maybe you went through these before, maybe you didn't. So if you're doing the method 2 that I did above, you need to kind of understand how numbers sort of work. And there's some really, I don't know if they're little tricks or if you've ever heard of them before, but they're a bit interesting at the very least, and they generally work for all numbers. So if a number is going to be divisible by 2, the number will have a characteristic. So if the last digit of our number is even, then it's going to be divisible by 2. Any number, the last digit's an even number, it's divisible by 2. There you go. How about the divisibility rule for 3? Does anyone know the divisibility rule for 3? It's a bit of a strange one. You might not have ever heard it before. I don't see anyone typing in chat, so maybe I should just let the cat out of the bag. If I add all the digits up in a number, so I take the sum of the digits, and I divide them by 3, then the number itself is going to be divisible by 3. So it's kind of a weird one. If you had a really big, long number, maybe like, 6 or so sort of characters long, like 373,422, if you added all those numbers together and they divide by 3, then that means the number is divisible by 3. Kind of a bit of a strange rule. A whole number is divisible by 4 if, this doesn't happen as often, but the last 2 digits are divisible by 4. So if you have a big, long number, doesn't matter what all the numbers are, if the last 2 numbers are divisible by 4, then the number is divisible by 4. 5, this one's a little more common. It has to end in a 5 or a 0. 6 is a strange one. Last digit is divisible by 2 and 3. Alex, I'm going to go ahead and say I didn't make up the divisibility rules. I know it kind of just is silly to add all the digits together and divide them by 3, and why not just divide the whole thing by 3, but sometimes these things are important. That's right, Abby. So when we're talking about these numbers, if they're really, really big numbers, the last 2 digits are divisible by 4, that means the whole number is divisible by 4. Just kind of little tricks. You don't have to memorize these, they're just here so you know. There's never going to be a question on a test that says, what was the divisibility rule for 9? And you think, I don't remember. So they're just here to kind of make things easier. If you've never seen these types of things before, then there you go. They're here for you. We're going to skip 7 because it doesn't have a really nice divisibility rule, so we're going to just ignore it. 8 is the last 3 digits, divisible by 8. Nine is kind of like 3, the sum of the digits, divisible by 9. And 10, you guys probably know that one ends in 0. And 11, we're going to ignore as well because it doesn't have a fancy rule like the other ones. So there you go. Some divisibility rules for you. If you're doing some factorizing and these things come up, then you can think, that ends in a 0. So it's either going to be divisible by 10 or 5. I'm going to divide it by 10 or 5. Or the last number is even, it's going to be divisible by 2. Or I add the 3 digits together and it's divisible by 3. Then it's going to be divisible by 3. Again, don't need to memorize them, won't come up a lot, not going to be specifically asked, but just might make your life a little bit easier, just possibly. All right, so the next couple questions are using some of the definitions we used up above. So the first one here, determine the greatest common factor of 126 and 144. You might see this written as GCF 126 144. All right, so what I'm going to do is I'm going to just do factor trees for both these numbers. I'm going to go 126, I'm going to do a factor tree for it, and I'm going to go 144, I'm going to do a factor tree for it. See where I end up. So 126, I'm usually pretty good at dividing by 2 in my head, so I'm going to divide that by 2. 2 and 63 gives me 126. 63 is going to be 7 and 9, and 7's prime, 2's prime, 9 is 3 and 3. So I know if I take 126 and break it down into 2 times 3 times 3 times 7, I have factored it. So 2 times 3 times 3 times 7 gives me 126. 144 now. We need to break this down using a factor tree. What are the prime factors of 144? So I know 144 is a perfect square, so I'm going to use 12 and 12 to start. I know 12 is going to be 4 and 3. And then 4 is going to be 2 and 2. So if I take 144, how am I going to get to that? That's going to be 2 times 2 times 2 times 2 times 3 times 3. So that is the prime factorization of 144. Your factor tree doesn't have to look like mine. Your branches can go in different directions. It doesn't matter. But that's where you should end up with. Everyone should always end up with the same prime factors for these numbers. Now, the greatest common factor is going to be a number that, if we looked at the factors or the factor trees, that is shared by both of these things. So what do both of these things have in them? So if I look here, I see that there's a 7, and I don't see any 7s over here, so I'm just going to ignore the 7. I see a lot of 2s and 3s. How many 2s and 3s are common to these things? Well, this one has a 2 times a 3 and a 3. This one also has a 2 times a 3 times a 3. That's common. They both share that. So if they had something like a 7, and there's a 7 over here, I'd include the 7. But because it doesn't have a 7, I'm not interested in it. So the greatest common factor of these things is going to be 2 times 3 times 3, which is going to be 18. So that's just one way of doing it. You can kind of do like a brute force method where you just kind of take 126 and 144 and you start dividing by bigger and bigger numbers until you find one that's common to both of them. So what do I mean by greatest common factor? If I go into my calculator and go 126 divided by 18, I'm going to get a whole number. If I go 144 divided by 18, I get a whole number. And that happens to be the greatest number, the largest number that'll divide into both 126 and 144 a whole number of times. A lot of times when we get to this sort of section, students get a bit confused. I don't know about confused. They kind of lose sight, maybe. They kind of get caught up in the process, doing the factor trees and trying to figure out what's common, instead of just kind of thinking, what is the greatest common factor? It's a number that divides into both of these things, so 126 and 144. So that's one way to do it. There's other ways. You can break it down, instead of using the factor tree, just prime division. That'll work as well. The least common multiple is the same sort of idea. So when we talk about the least common multiple, we're talking about a number that both of these, we're going to use 3 in this case, that these 3 things multiply to. So I'm going to show you 2 different ways. Hopefully they both fit. So this is method 1. And this is going to be done this way. We're going to list all multiples until the same one appears. What do I mean by that? Let's start with 28. Multiples of 28, what are they? So if I go 28 times 2, I get 56. If I go 28 times 3, I get 84. 28 times 4, 112. Times 5 is 140. So I'm just plugging these into my calculator. 6, 168. Maybe we'll go up to like 200. 7 is 196. And then 8 is 224. I don't know how many I need to do because I haven't done the other numbers yet. I'm going to do the same thing with 42. And then I'm going to do the same thing again with 63. And I'm looking for a number that's shared by all of them. So if I go 42 times 2, I get 84. And I'm thinking, I see 84 has appeared here and here. Maybe that's the one I'm looking for. Maybe it's not. I still have to do the 63. 42 times 3 is going to be 126. Times 4 is 168. Times 5 is 210. So maybe I'll just go to 210. 63 times 2 is going to be 126. So that 84 doesn't work. These both share 126, but the 28 up here doesn't have a 126 in it, so that's not going to be it. All right, I got to keep going. 63 times 3 is 189. Do they have 189? Nope, none of the others do. 252. I'm up to past the other ones already, and I still haven't found a common multiple of them. So maybe I'm going to go back to my 28 and my 42 and see if I go a little bit higher what I end up with. So 224. The next one, if I add another 28 on there, I get 252. How about this one? If I add another 42 on there, I get 252. So I see that all three of these terms will eventually multiply to 252. Is there any number that was smaller than 252 that they all three multiplied to give me, or multiples of them would give me? There isn't any. This 84 appeared here and here, but it didn't appear in the 63. 126 appeared here and here, but not in the 28. 168 appeared here and here, but not in the 63. So the only one that works is the 252, because all three of them will eventually multiply to 252, and that's the smallest one. So that's one method. I kind of took a long time to do that, but it's kind of a method that will eventually get you there, but it can be really messy because sometimes you'll be dealing with really large numbers. So that's method one. This is method two. And we're going to use prime factorization. We're going to take the greatest power of each number and multiply them. So this might not make a lot of sense right now, but we'll get there. All right. My three numbers. I had 28, I have 42, and I have 63. I'm going to take factor trees for all of these things. So this is where you get to test your math skills and how good you are at multiplying in your head, breaking these things down. 28, it's going to be 4 and 7, and 4 is 2 and 2. So there we go. It's factored to primes. 42, a bunch of different ways you could break that down. I like 21 and 2, 21 is 7 and 3. 63, 9 and 7, 9 is 3 and 3. All right, I have figured out what my prime factorization looks like. I'm going to write this like this. 28 is equal to 2 times 2 times 7. which is the same thing as 2 squared times 7. 42 is equal to 2 times 3 times 7. And 63 is equal to 3 times 3 times 7, or 3 squared times 7. Alex, you're asking a question. 2 squared times 7 is 28. Why not write 28? The idea here is that we need to break down the prime factors of these numbers to figure out the least common multiple. So it's kind of a means to an end. We have to figure out what the prime factorization is before we can figure out the least common multiple. So if I go back up to kind of how I defined what we were going to do here, method 2. It's use prime factorization and take the greatest power of each number and multiply them. So I'm still trying to find the least common multiple of these two things, the LCM. I'm going to take the greatest power of each number. So I'm looking, I see 2. Okay, what was the greatest power of 2 I had? I see I have a 2 squared here. So I'm going to steal that 2 squared. And I'm going to start with 2 squared. And then I had a 3 squared over here, so that was my 3. And then what else did I have? I had a 7. Are there any factors I missed? I have a 2, I have a 3, and I have a 7. That's it. The greatest exponent of 2 was 2. The greatest exponent of 3 was 2. The greatest exponent of 7 was 1. If I had another prime in there somewhere, like a 11 or something, I'd include it, and then whatever exponent it had. So what is 2 squared times 3 squared times 7? I don't know that off the top of my head. 2 squared is 4 times 9 times 7. It's going to be a big number. What do you think? What did we find was the least common multiple up above in the first method? These things all multiply together to give me 252. And that is exactly what I had from method 1. So maybe that kind of helps you out a bit, Alex. It's just a way to get to where you need to go. So, you know what? In chat, I want you to write which method you like better. Did you like method 1 better or method 2? Just need to put in a number, 1 or 2, and then hit enter. What do you think? 1 or 2? 1 or 2? 1 or 2? Chloe's going with method 2. Taylor likes method 1. Not sure yet. You're undecided. So there's no right or wrong way to do this. I will tell you that method 1 is easier for smaller numbers, but when you get really big numbers, like find the least common multiple of 733, 421, and 5,000. The numbers get really big really fast, and it kind of just is a bit messier, I guess. The second method will always work, just factor trees and go from there. So I think the general consensus among the class is that 1 is maybe looking a little bit easier. And I mean, you can do it either way, you'll end up at the same spot. So the second method is probably a little bit faster, and you'll eventually kind of maybe learn to love method 2. Method 1 works, and that's probably what I would do. Isn't the lowest common multiple for all numbers 1? You're kind of getting mixed up with multiple and factor. The a factor that goes into all numbers is 1, yes, because all numbers are divisible by 1. But when we talk about multiple, like multiples of 4 would be 4. So 4 times 2 is 8. Then we go 12, 16. So multiples are taking that number and multiplying it. So if I wanted the lowest common multiple of 4 and like 12, I'd go, okay, 4 times 2 is 8, and 4 times 3 is 12, and 4 times 4. And then I do the same thing with 12. I go, okay, 12 times 2 is 24, and 4 goes into there. So the lowest common multiple for those things is actually going to be bigger because we're multiplying them. If we're talking about factors, we're going smaller. If we're talking about multiples, we're getting bigger. Kind of a bit of a different idea. Next thing here is talking a little bit about algebra tiles. Now, maybe I shouldn't say this, but I'm going to because I just am going to. I hate algebra tiles. Put a green check in chat, please, if you have used algebra tiles before. And if you have no idea what I'm talking about, you can put in like a red X or something like that. So just in chat, green check if you've used algebra tiles before. Looks like we have a few people that have used them. For those of you who didn't put in green check marks, could you put in a red X if you've never heard of algebra tiles before? Just so I get a bit of a feeling for where we're kind of at with the class. Algebra tiles, never seen them before. These are them over my my right shoulder here. It's kind of, it might be a sign of the time that I learned math. It was just something that, I never saw. And when you get into the like younger math grades, I think 6, 7, Math Makes Sense textbook, they have algebra tiles in there, and they actually are in the grade 10 curriculum. And they actually have questions on provincial exams using algebra tiles. They'll have these algebra tiles there for you, and they'll ask questions about like diagrams of algebra tiles, like what polynomial does this represent, or things along those lines. So in chat, it's looking like we have, can't read the number, about half the class has seen them before, one person's never seen them, and then the rest are off in their living room watching TV maybe. So about half of you guys have seen them, which is probably about normal. I strongly dislike them. I don't think the amount of time we put into teaching you guys how to use them is valuable in terms of what you'll get out of them. If you move forward with math into grade 11 and 12, generally speaking, you won't see them a lot again. And some of the things we do in grade 10 math, using them, the rules actually don't apply. The rules of using algebra tiles don't even work for factoring sort of negative numbers and things like that. So I find some students really like them because they're maybe visual learners and they kind of make things easier, break things down for you, make life easier. I personally believe that they just make your life harder. Maybe that's just because of how I learned math. I'm sympathetic to those of you who like using them. I think it's a great way of visually showing how to do math, which is perfect, but I don't love them. In fact, I asked a bunch of other teachers if I could borrow a set of algebra tiles over at our other building, Central, and none of them had them at the other building. They don't even have them over there. They just, don't really get used that much, and very few students generally like using them. So if you want to do some algebra tile stuff, go for it. I'd be happy if you want to express these things using algebra tiles. I don't have anything wrong with that. You can use them. In fact, I can pretty much guarantee at least one question on your provincial exam will have an algebra tile type question in it. I'm not going to spend a ton of time talking about them or using them because I don't think they're very valuable here. So this is just my opinion, and I apologize if you love them and you think you're going to benefit a lot from them. Maybe we can get a little bit further into factoring polynomials, sorry. Maybe I'll show a couple examples of them, but for now I'm just going to kind of breeze through them. You'll see in the learning guide they actually do appear, And if you want to do some questions with them like that, by all means, go for it. But I'm not going to insist that you use them. So that's just kind of how I feel about them. And if you want to use them, there's nothing wrong with that. I don't have an issue with that. So take it for what it's worth. I'm going to skip this little guy here. This actually starts to get into factoring just a little bit. And maybe I'm just going to leave it there for today. Because I don't really want to start this whole factoring thing right away, because this is kind of the meat and potatoes of Unit 4. So I've kept you guys a few minutes late yesterday. I'll let you out a few minutes early today. Today's Tuesday, so you have English at 11:30, so in about 15 minutes. And we're just going to leave it there. In terms of the learning guide, how far did we get? You can see the next section, algebra tiles. I'll go through the answers to these if you guys want. If you don't want to do them, then I guess you don't have to, but they do come up on the provincial exam, so it's worth at least going through these. So maybe we'll go through those when we have some time later on. Expanding special polynomials should be good. We've done examples of those things. So you should be up to page 8 now. This is lesson 4, should make it up to page 8. Yes, Abby, I mean 10:30. Sorry, I looked at the end time, not the start time. So learning guide, you should be up to page 8. I understand you're probably preparing for the midterm. When I think about the midterm, you guys have already learned all this stuff, so I don't want to spend a ton of time, but I will dedicate as much of tomorrow's class as you need to going over the learning guide for the midterm review. So whatever you guys want me to do next day, I'll just say Unit 4 is on the back burner for now. Whatever you want to learn, relearn, go over from the first 3 units, 1, 2, and 3, and then the beginning stuff of 4. I'd be happy to do that. So that's kind of what we'll do next day. So I'm going to dedicate the whole class to that. Alex, I will go over that next day. I'm just going to do problems all day next day. I let you guys, or I kept you a bit late yet last day, and I'll let you out a bit early today, so it all kind of adds up. So there you go. That's all I want to say for now, and I will see you guys tomorrow, and Mrs. Ward will be on shortly at about 10:30. So have a good afternoon, guys, and we'll see you tomorrow.